Hi friends, welcome back to Edupedia World. Today we'll be starting discussion on a new topic on current electricity, and we'll see what is a cell and some terminologies related to cell, namely what is electromotive force. We'll understand the whole concept. Then we'll see what is terminal voltage and compare and contrast the two and see what is the basic difference between EMF and terminal voltage. And we'll close the chapter by discussing internal resistance and factors on which internal resistance depends. So let's start with EMF. An electric cell is a device which is used to maintain a constant potential difference. Now, how does the electric cell do it? What it basically does is through reactions, chemical reactions, it provides a source of continuous generation of electrons, and the flow of electrons from one terminal to another terminal leads to a potential difference between the two terminals. Let me show you figuratively how we design a electric cell. So basically there will be electrolyte, which will be a conducting liquid. It can be many different things like dilute, sulfuric acid, depending on our need and how much potential difference we need to create. Now there will be what is known as electrodes, two plates, electrodes. Okay, one electrode and the other electrode, and these electrodes will then come out of the cell, and these are called the terminals of the cell. So basically one of the electrode will be positively charged. Let's say this is our positive terminal, and the other electrode will be negatively charged. Okay, now this electrolyte here, with the help of the electrodes, will undergo chemical reactions, and that will result in a flow of electron from one terminal to other terminal, leading to a difference in potential. So this is the cell. Now what is the potential difference between the electrodes? The potential difference between the electrodes can be thought of in two ways. There are two electric potential depending on what condition we are thinking about. One is called the EMF, or the electromotive force, and second is called the terminal voltage. So what is both of them, and what is the basic difference between them? Why do we need two potential difference? So let us start with electromotive force. What exactly electromotive force is, that if you do not connect the circuit, if you do not close the circuit, that is the terminals are exposed like this, there is no further circuit for the electrons to have a closed path, then the potential difference that is existing between the terminals is known as the electromotive force. Okay, therefore electromotive force can be defined as if no current is drawn from the circuit, that is the circuit is open, then the potential difference between the terminals is called electromotive force. Let me write it down. No current drawn, then PD across the terminals. That is my electromotive force. Now in this particular scenario, what will it be? In this particular scenario, this is my electromotive force, given we have not closed the circuit. and electromotive force is denoted by epsilon. This is called epsilon. Okay. Now we have seen electromotive force, we understand what it is. Then what is terminal voltage now, and how is it different from electromotive force? To understand that, let us see a closed circuit. So let's draw again the whole thing, the electrolytes, the electrodes. Okay, these are my terminals. Now suppose that we attach a resistor to this terminals. This is the symbol of a resistor. Now what is happening here is, let's say this was the positive terminal and this was the negative terminal. These are the electrodes, this is the electrolyte. Now if we attach a resistor, what is happening is the circuit is getting closed. There is a complete loop for the electrons to flow. Electrons can be generated here, suppose. Then it can basically go from the electrons can flow from the negative terminal to the positive terminal, or the current can flow from the positive terminal to the negative terminal, and the whole circuit can be completed. Fine. Now what will happen is, this is a situation where current is drawn from the circuit, isn't it? The cell is providing current. Let me write it down. The first one, no current. In this case, current is drawn. Current drawn. Fine. So now since current is drawn, what is happening is that the difference in potential between the terminals now is different than what was here, and this difference in potential in this scenario is known as the terminal voltage. So this is my terminal voltage denoted by a capital V. So to define terminal voltage, the potential difference across the terminals when current is drawn from the cell. Fine. So we see that electromotive potential of the cell is when no current is drawn, and when current is drawn we have terminal voltage across the terminals. Now let us see how these two compare. Fine. But before that, let me briefly mention you that a cell is represented like this. This is a symbolic representation of cell, where the longer line is the positive terminal and the shorter line is the negative terminal, and these are my terminal ends. So basically this is this end and this is this end, and if we attach a resistor to it, in this scenario, we just need to attach a resistor over here like this. Fine. So now that we are clear of the convention of the drawing, let us see the definition of electromotive potential and terminal voltage in a different sense, in the term of how much work is to be done. So electromotive potential in terms of work is defined as the energy required per unit charge in taking a positive charge around the complete circuit of the cell. Okay, so EMF in terms of work done or energy spent is the amount of energy required to make a positive charge do a complete circuit travel through a complete circuit. Therefore, EMF epsilon is defined as, let's say, W amount of work is done to move a Q naught charge, then the EMF is work upon Q naught. Whereas in case of the terminal voltage of a cell is defined as the amount of work done per unit charge when a positive charge is moved around the circuit connected across the terminals. Okay, so when it has to move from here to here, then the amount of work needed to be done is the terminal voltage. Whereas for EMF, if it were to complete the whole circuit, then the amount of work would have been the EMF. So terminal voltage in terms of work, capital V, let's say W dash work is required to be done for the circuit positive charge to move from here to here, then W dash upon Q naught. Fine. Therefore, what we see is there is a disparity between EMF and terminal voltage, and that disparity comes from the amount of work that needs to be done on the electron to move from one of the electrodes to the other electrode, right? Since EMF is throughout the circuit, terminal voltage is only across the terminal. Therefore, there has to be other work which has to be done to move it from here to here to complete the circuit, right? And let's say the amount of work required to move the positive charge from here to here is small w, then my additional voltage drop inside the cell. The voltage drop in cell is equal to, let's say, small v, and that can be small w upon Q naught, right? So this is my voltage drop within the electrolyte. This is my voltage drop outside across the terminals, and this is my total voltage drop. Given these factors, given these three things, what I can write is that EMF E is equal to terminal voltage V plus voltage drop across the cell, isn't it? From there, W upon Q naught is W dash upon Q naught plus small w upon Q naught, isn't it? Basically we are trying to find out that this has to be the relation. So by this is from energy conservation. So total work, that is this, should be equal to this work plus this work, and this total work is our EMF. Therefore EMF is this V plus small v. That gives us the relation that the total EMF drop is terminal voltage drop plus voltage drop across the cell, right? This is just to give a mathematical proof of what we already visually observe here from the theory. Fine. So now you will say that it's okay, we understand what the EMF is, what the terminal voltage is, but why should there be a drop across the cell, voltage drop inside the cell? That is because every battery has something which is known as internal resistance. Let's see what internal resistance of the battery is. Internal resistance. Now imagine that the electrons or the charged particles will have to move across the electrolyte to complete the circuit, isn't it? Now obviously, since the particles need to move, there will be a resistance offered to the movement of the particles. Now this resistance which is offered to the movement of the particle manifests itself as the internal resistance of the cell, right? So like parallel to the concept of resistance for a wire, the electrolyte and the cell in general will offer a resistance to the flow of charged particles, and that is the internal resistance. Now if the internal resistance of the cell is small r, then this potential difference V can be written as I times R. This is from Ohm's law, where I is the current which is flowing through the circuit. So if I current is flowing through here, the same current needs to flow through here for the circuit to be complete. Therefore my internal potential drop, that is the voltage drop within the cell, is current times the internal resistance. Therefore what we see is more is the current drawn from the cell, more is the potential drop inside the cell, isn't it? Because the resistance needs to be consistent. Therefore if we use this information and we plug it back here, what we can see is this. What we can see is, we know E is V plus small v. Now small v I will replace with I times small r, and capital V I will replace with I times capital R. Let me draw the circuit again. So my circuit, complete circuit will be, this is my battery and this has an internal resistance of R, right? So I can show the whole battery system like this. This is my battery region, and then I am adding external resistance to it of resistance capital R. Okay, capital R, this is my small r, this is my epsilon. And as a result of this, let's say we have a flow of current of magnitude I, then the potential drop across this resistor will be IR, isn't it? Across this resistor will be I small r. Therefore I can replace and write epsilon as epsilon, capital V as I capital R, and small v as I small r. And then if I take the IR in the other direction, I can write I small r is epsilon minus I capital R, and that gives me the internal resistance of the battery equal to E minus IR upon I. That turns out to be E by I minus R. Okay. Also I can alternatively write this as, let's do it. If I take this and I replace IR by capital V, then E minus V, and this I can write as, we know V is equal to IR, so I can be written as V by R, and that will give me E minus V divided by V by R, which is epsilon by V minus 1 times R. So these are some of the ways in which the internal resistance of the battery can be expressed in terms of the potential drops. Fine. Now that we have seen what is the internal resistance, and now that we understand that this presence of this resistance here leads to a potential drop across the terminal which is less than the EMF of the battery, let us see the factors that can affect the internal resistance. So factors that will affect the internal resistance is, one, the type of electrolyte that is there, okay, nature of electrolyte, Second is the surface area of electrode. The more the surface area of the electrode, more will be the path available for the ions to move, and less will be the internal resistance. Third is distance between electrodes. So more is the distance between electrodes, more will be the resistance encountered, therefore higher will be the internal resistance. And finally, the temperature of the electrolyte. Temperature of the electrolyte, how is it related? Higher is the temperature of the electrolyte, less will be our internal resistance, because the movement of the ions can be easier as the viscosity and other factors of the electrolyte changes. So basically you need to know that with increasing temperature the internal resistance will drop. Fine. So this gives you an idea about the concept of potential difference and internal resistance. With this background, in the next class we will start studying about resistance in parallel and in series. Till then, have a great day. Goodbye.